My name is Noam Rosenthal. I'm working at Wix, where we have millions of users' websites. At Wix, I'm in charge of the mobile editor or the mobile client, making sure Wix websites work well in mobile. Before that, I was working on browsers. I was working on WebKit and on Safari and on mobile browsers inside Nokia, and working a lot with front-end developers to make their sites work great. At WebKit, I was working specifically on graphics. And actually, some of the tricks I'll show you here, I put them into Safari. So that's how I got into it. I'm developing front-end for many years, and I love both working inside the browser and outside. Now, this presentation is called Browser Graphics Under the Hood. First of all, the agenda for today. We'll have one presentation that is a little more theoretical, but very practical, but less hands-on about browser graphics, how they work, why we do certain things, so to give you a little background and enrichment. The second one is about specifically about how to write mobile galleries, specifically a few tricks that I used in my own mobile galleries that I wrote for this. The third part is hands-on, where we will take this boilerplate repository that I prepared, and we'll try in the few hours we have to take some of those tricks and make a nice-looking, fast mobile gallery. We'll do it however much we make and try to learn from it. So this first part, the browser graphics under the hood, I explain about how things work inside the browsers and how we can take advantage of them. First, why crawl under the hood? I used to have very long hair, so when I go under the hood of the car, it gets really smoky and stinky. So I usually rather not do that, and rather give my car to a mechanic. This is when I'm just a driver, but when I'm a professional driver, I have to know how my engine works. We as front-end developers are professionals. We are like professional drivers in the browser world. We use the browser as professional. Sometimes we get to where we need to deliver something. There is no browser mechanic to give this problem to. Also, I know from experience that browser mechanics charge a lot, like regular mechanics. So sometimes when you're professionals, everything relies on you, and you have a deadline. And at a particular point in time, you have to find a fix. And knowing how the browser engine works under the hood will help you find those little fixes at the time you need them, I hope. So I will start with the rendering pipeline 101. Understanding the rendering pipeline, how one thing leads to another inside the browser engine when you render things, when things go on the screen. The terms I use here are also the same terms you would see when you open the Chrome DevTools, the Chrome timeline. You would see the same terms, so they'll be familiar to you if you use the Chrome timeline. The first part of the rendering pipeline is the style. Style, in the Chrome timeline, it's called recalculate style. Now, what does recalculate style actually do? It combines three main things, maybe more that I forgot, into one. So the three things are the actual DOM. We have the DOM tree with all the HTML tags, probably many divs, but other things as well. So it knows your tree structure. It takes your CSS, everything you put in your own CSS. And it takes a third thing, which is state. The state, for example, hover. All the pseudo elements of hover, the media queries have to do with state. Your screen can be at a different ratio. So those states affect the CSS. What style does is something very particular. It takes all those together and defines the actual style of a particular element. So it takes care of all the cascading, of all the states, of all the CSS rules, does that. This is what happens when you do, for example, when you call get computed style. When you call get computed style, it actually combines all those things together and returns you the CSS of a component. So this is recalculate style. Now, what recalculate style does not do is figure out relationship between different objects. It takes every object on its own inside the DOM hierarchy, but it doesn't calculate the relationship. Who does that is layout. We hear the word layout a lot when we deal with front end. Layout does also something very specific. So I want it a little demystified of what it actually does. The responsibility of layout is to turn every element into renderable, absolute positioned components. Many times, what we show in what we use in the front end is rules. We use flex. We use all kinds of positioning. We use tables if we're from another century. We use horrible things like floats. What the layout comes to do is to take every element, take all those rules, take the other elements, and define the rectangle, the actual absolute positioned rectangle for each element. That's what layout does. It actually takes three things into effect again. One of them is content. You're in a blog, you have a text, and you have an image with float right. The text could change, maybe the float would not change. So the text and the actual image would be content. If the image natural size changes, it could change the layout. That's content. It takes rules, whatever you put in your CSS and the style. And it takes the viewport. You have the VW coordinates. You have things that attach to the screen. So layout is a complex procedure. Just think about how many CSS properties you have that affect it. It's a lot of calculations. It doesn't make it makes it expensive, but it doesn't make it a bad thing. Layout is a good thing. It's what allows the web to be the web. Because of this, there are two main things that are dynamic about the web. One is that there is a lot of content. The content is very dynamic. You have publishers producing news. That's dynamic. You have users uploading content today in Facebook, in the social networks, video. All the content is dynamic. This is why it's web. The content is dynamic, right? We have some publisher, we have somebody producing it. It changes all the time. We have media changing. People browsing with different mobiles, with different computers, with their computers set up differently, with different browsers. That's viewport. So those things are not as dynamic in apps, for example. When you have an app, the content is usually not as dynamic. If you change the app, you have to ask the user to re-download it. It's a lot more complicated. So those things are what makes the web what it is. What the rules give us is an anchor, some place where we can be stable in our own place. We say, given this content and this viewport, this is what you should render. So rules are the CSS and the things you put in your DOM. Those are the rules for viewport. Those are the rules for layout. So putting something as float left, that's a rule. Putting a few elements in a flex, that's a rule. Them together with the content and the viewport will give you an absolute position for everything. The browser can render it. Now, because this deals with complexity, layout is the complexity of the web. It's also expensive. It's an expensive operation. It usually deals with the relationship between many objects. It doesn't scale. When you have the more elements you have, the slower layout is because of all those relationships, all those complexities. So when we use layout, we need to be very careful that what we do has to do with the dynamics of those things. With the viewport is dynamic, the content is dynamic. If they are not, for example, the content didn't change, the viewport didn't change, but you have some UI, you have stuff moving around. Usually, no need to if you can avoid using layout stuff for that, great. The third part, for older browsers, let's say until iPhone 1 or 2, and this was the third part, and still in many cases the third part. Paint is what actually changes pixels on the screen. Think what actually happens when you paint pixels on the screen. You have an LCD driver or a LED, whatever. You have a screen driver. It has to change the amount of voltage for every pixel. For large screen computers, you have 4 million pixels, let's say. 4 million pixels, every pixel is 3 bytes. So you have 12 megabytes of data change for a full screen update on a big computer. Less than that on phones, but still. That's 12 megabytes of data that has to go with each frame. So Paint is what does that. Now, today computers have very nice ways to copy large amount of data, of block data, like a copy to the screen, like an image. But Paint has to deal also with more complicated things. One of them is text. How many of you know, does anybody know how many text attributes there are in CSS? I don't either. It's too many. It just the amount of stuff you can do with controlling text with rules for text is immense and uncontrollable, especially if you add the undocumented things. Same with SVG. SVG spec is crazy with lots of things. So rendering has to, the painting has to deal with all that. So painting is also taking all that stuff, changing it into a block of pixels that can be copied to the LCD driver is a heavy operation. This type of operation is called rasterization. It's commands into pixels is rasterization. We'll use that a little bit. Now, we said that copying blocks is pretty cheap, but text, especially, let's say, complicated text with outlines and things, is more expensive. Now, let's take this cute bunny. The bunny is moving. The bunny is a block, right? It's a block of pixels. The grass behind it is a block of pixels. But above the bunny is some text that might be expensive to draw. And the text has opacity. Now, what happens here if we paint the whole screen with every update? The area where we have text, we'll have to redraw everything. We'll have to draw both the grass and the bunny again, because it has to blend them. It will have to draw them for each frame, even though the text itself didn't change. Right? So we have to make all those outline glow calculations, crazy calculations for each frame, even though they didn't change. They didn't change at all. The text didn't change at all, just because the bunny moved, which is unrelated to that. So this was a problem in trying to put fast animations on the web. Who solved it nicely was Apple, and now everybody uses it. It's called compositing. Probably a lot of you heard of it. With how many of you have used the Translate Z or Translate 3D trick because somebody told you maybe it will be faster? What compositing actually does, I like to think about it as transparent paper cutouts. So it would take parts of our tree, of our DOM, that are going to move around, but their contents are not going to change. It's going to cut them out of the main paper, of the main screen, draw into them once, and then just move them around like a block. If we go back to the bunny, we will keep the grass as a background, but we will have two paper cutouts, one for the bunny, one for the text. We draw once into the text. We calculate all the expensive outline, glow stuff. Then we have it as a bitmap. We cut out the bunny also as a bitmap. And then we just copy, 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 copy. That's what compositing does. It's an optimization that converts complicated painting into blocks. This goes to the next point about the GPU. GPU is the graphics accelerator of the computer and of mobiles. Many times I've heard front-end developers say, you should move it to the GPU, it's faster. It's a very direct metaphor that it accelerates, therefore it's faster. So this is actually not true about the GPU. So the GPU is a slower computer than the CPU. It's a slower unit than the CPU. It's lower power. It's cheaper. The CPU is actually a very strong unit, a very strong core. The GPU is much weaker. However, it has one significant difference that make us want to use it, but use it wisely. I like to think of the CPU as a Jedi, and the GPU as 1,000 stormtroopers. So can you say whether a Jedi is better than 1,000 stormtroopers? It really depends on the situation, right? If you want to find the secret plans and kill the main bad guy, maybe you want a Jedi. But if you want to scatter around the whole desert planet and find the droid, maybe a Jedi will take a long time to do that. And you want to take each stormtroopers to go like this over a little spot of land until one of them finds the missing piece. So this is the same for CPU and GPU. Even though GPU cores are weak, there are thousands of them in a GPU. Each one of them can do little commands, just a few mathematical operations. But when we program to the GPU, what we actually do is that we give it a command to take big blocks and conduct the same mathematical functions on them with different parameters. This is how we work when we work with OpenGL. We prepare a big command, and we apply it on a big area. If we're back to the bunny, when the bunny moves, what happens is that we actually put the 3 layers of it in memory. and the GPU, and we give commands to the GPU to copy them, to copy them one on top of the other and blend them, each time with a different parameter of where. When this happens, that's what actually happens in the GPU. What happens when you do a lot of paper cutouts? Maybe your drawing is faster, but you use a lot of paper. So in our case, so paper cutouts are not that good for the environment, maybe. In our case, this is memory. Whenever we do all this translate Z stuff or mess around a lot with compositing, we have to take care of memory. Many times optimizations in the software in general, and specifically in graphics, have to do with weighing performance, like runtime performance versus memory usage. Many times this is a problem in computing. In case of compositing, whenever we start going into compositing world, we have to think in our head in computing terms. Say, okay, I'm going to actually allocate a block of memory for this now. Now, what happens if you don't do that? Basically, you're in a world of pain that's going to come later. So out-of-memory issues, low memory issues are issues that always come later. They come they usually look something like insufficient resources. You see parts of the website that are not rendered and you don't know why. You see all kinds of tearing. The browser crashes. Things that are very hard to debug and deal with, are hard to analyze. Also, modern operating systems are very good with trying to crunch more memory. So it's very hard to also measure memory and how much memory things take. Even though we're in a web world and things are higher level, and we don't manage memory in JavaScript really. Everything is garbage collected. When we think about graphics, we have to go back more to the world of computer science. Think about memory, think about resources, not just try things, plan it. He's asking how to make text behave like a paper cut. So I like the property will change, and I'll show in the demo how I use it. The usual trick today is to use translate 3D or translate Z. When something is 3D transformed, the browser thinks of it as something that's going to move around. Now, if I could take one key to performance about why the GPU works better is concurrency. The GPU works better where we can offload stuff to it, and it can do stuff in parallel. The GPU does many things in parallel. It takes the 1,000 cores, each one takes a few pixels, and does them in parallel. So especially when we do things in mobile, we want as much stuff to be parallelized. GPU is one way to do that. There are also other ways. In the next slide. The last player in the rendering pipeline is the watch, the clock, the aspect of time. One of the things I love most about software engineering is the time aspect, the time domain, how to manage what happens after another, what happens in parallel. I love dealing with that. In the browser, you actually have many clocks and many things that happen in parallel. You just control them separately. The main things in the browser happens in the main thread of the browser. This is the main clock. When you calculate style, when you do the layout, they all happen in the main thread. Why that happens? is because the DOM, the JavaScript, and the layout are very tightly connected. We talked about getComputedStyle, and getComputedStyle from JavaScript. Let's start with it. JavaScript is not multi-threaded, so you're usually inside the JavaScript thread. So anything that requires JavaScript access also needs access from the main thread. When we talk about style, you have getComputedStyle. You have to find out the actual style of things from JavaScript. You can't really offload style calculation. You have also JavaScript that relies on layout. Get bounding client rect relies on layout. Offset client top of anything relies on layout. Actually, every time you call one of those things, it makes sure layout has already been done. So one unwritten trick here, or let's say rule of thumb for layout. Don't do read write with layout. If you do something that changes layout, don't read it right afterwards. Change everything you need and then read it back, or the other way around. Because what happens is that if you change the layout and then you read, it will have to relayout. So this is an easy-ish trick. We use it at Wix. It's extremely important for us because in the editor we have tons of elements. So that's partly how we do with it. Even in the main thread, we have two main clocks, or two main timeouts. One is a set timeout, and one is the request animation frame. Set timeout, the difference between them is that set timeout is the at least timeout. When you say set timeout for 2 seconds, it means to the browser at least 2 seconds. It wouldn't come before that, but it could come after that. When something is in the main thread, you cannot guarantee anything. There are things that are beyond your control. One of them is garbage collection. You can try to help garbage collection by better managing your memory in JavaScript and using good libraries. However, you can't completely control it. JavaScript can decide at any point to garbage collect and will stop your main thread. So if you do things in there, they might be choppy, even if your JavaScript is extremely fast. Think of it as Usain Bolt, very fast, standing in the line for the post office. Doesn't help him how fast he is. So that's what happens when you do things in the main thread. What's nice is that in the browser, we actually have many other threads. We just need to access them and use them. One of them is, of course, workers. When we have heavy operations, computing operations, things that have to do with databases, we can move them to the worker, and then we free up our own main thread. Great. The other one is compositing. Actually, when we move that bunny, a lot of that happens on a different thread than the main thread. So things you do in JavaScript, if you do things right, and I'll show it in the demo, if you do things right, things you do in JavaScript will not bother or be bothered by animations. Because they happen on totally separate thread. Same thing with scrolling on mobile. When you scroll the viewport in smartphones, in Chrome and Safari, the scrolling actually happens on a totally different process. What actually happens is that we have two processes or more. And we have a IPC between them. We have inter-process communication between them. So they work separately in parallel. Also, one of them can crash. That's what happens in Chrome when you see the oh snap thing. So we have IPC between them. This is called the web thread. And this is called the UI or compositor. On different browsers, it's a little different, but it's usually similar architecture. What happens in the web thread is that it takes tiles parts of the screen that it knows it's going to have to show, and renders them into memory. So we have the whole viewport of what we see, and a little more. The web thread takes a tile, renders into it. Takes another tile, renders into it. What happens in the compositor thread is that we just know the tiles, and we use the GPU to paint them in different areas. Even though painting can be expensive, it's totally separate from scrolling. We paint into tiles, and then we just handle the tiles in the compositor or UI thread. So whenever we can let the browser deal with scrolling, instead of doing stuff in JavaScript ourselves, for example, the better. I'm going to show you how some of this works in practice on animations. What I'm going to show you here is lemmings falling. Anybody remember the game Lemmings? A little bit. I wanted to drop lemmings because it's not nice to drop actual animals, and lemmings are there to be dropped. I'm going to drop them in several different ways. They're all going to look the same to us, but they actually do something different in the browser. You all can get this code, by the way. It's a nice tutorial for how to animate things. Here I'm going to control, in the buttons, I'm going to control how the lemming is dropped. Here it's going to drop. And here we're going to show what actually happens in the code and what it makes the engine do. So layout. Can anybody see the code? Should I increase it? It's OK? I actually changed the margin left and margin top of the lemming with every frame, right? And these are request animation frames. So what happens in the engine for each frame is that we request animation frame, but that time we're in JavaScript, which means we're already on the main thread. So it could have already been blocked by something else, by garbage collection, by layout, but by anything else that happened on the main thread. We calculate the style. Remember, we take bits and pieces of what changed in CSS and in the viewport, and we calculate the actual element style. In this case, we layout. That's because we changed margin left and margin top of the lemming. So this is an expensive operation. And we rasterize. We probably paint with the CPU. Now, if I go to the rendering tab of Chrome, very useful. I turn on paint flashing. I click on layout again. You see that with every frame, I actually paint the whole box, the whole canvas. This is because it needs to be relaid out. Very expensive. Think of how many pixels it needs to copy. There is a gradient here. It has to do the gradient again with each paint. Very expensive. On this super MacBook Pro, it's fast enough. But the MacBook Pro is your enemy. You want to debug it, make sure things scale. Not get to them when your users complain about things not working well on their mobile. So look here. If things look ugly here, then they're ugly. Now, a different way to moving the lemming is a regular translate. What I do here in the code is I just change the transform of the lemming with every frame. You see here how it still needs to repaint the lemming, but it only repaints the lemming and the area around it. It does not paint the whole canvas. It also does not layout. You see there is no layout here. This I'm not making up. You can check in, if you run this in the Chrome timeline, this is what you would get. You would either get layout or you wouldn't, or you can check it. And you can check your code that way. This is easier to show in a presentation. So in this case, I do not layout. Why do I not layout? It's because transform is a cheat. Transforming elements, instead of changing their left top or their margins, has no effect on other elements. It's just changing pixels. So it's also limited because of that. But it allows us an optimization. That means that if one element changes its transforms, it does not affect anything else outside the scope of this element. This is why transforms are optimized. It's because they have no side effects outside the current DOM node. Now, we have a similar way to do that with top left, which is position relative. When something is position relative, it's very similar, or even absolute. It's similar to transform in the sense that it shouldn't affect other DOM nodes. It does have one big difference, which is a subpixel text. When you have text, the browser needs to do a lot of corrections on it based on where it's located. Many times you move it by half a pixel somewhere. You do top or left 5.3 on text. How should it look versus other things? That's subpixel positioning. That's something that happens during layout. Transform does not deal with it. So if you transform things, if you use things for transform, it might be better to do it only while moving them. Otherwise, your text is blurry in certain situations. It just doesn't do it right. That's why also position relative still creates layout and transform does not. Now, when should I use layout instead of translate? For example, here, I count this lemming and the screen as content. It's dynamic, it changes, and it affects the rules of my entire page. So when I have a whole bunch of rules in the page that have to move around, if I would calculate it myself in JavaScript, it's not going to help me much. Let's just let layout do its own thing. It doesn't really matter. Usually, we just don't have pages that look like this, where the whole rules of the page animates. If you do, consider not doing that in mobile. Yeah, if you have changing UI, like a sliding menu, many times you use transforms for that instead of changing the layout in real time. It's usually the better idea. Think of it, is this a content change? Is this a content change or is this a UI change? As a rule of thumb, content changes I deal with layout, UI changes I deal with transforms. But nothing is black and white. This is like where I start from. Will change. Will change is the same as doing translate 3D instead of translate 2D. It's just more readable. It means will change transform means this component is going to move around a lot. We give the browser an optimization hint. What it does actually, same as translate 3D, is the paper cutout. One thing about will change, it does not work in Explorer. That's why many people still use translate 3D or translate Z. In this case, we have a paper cutout. If we look at it with paint flashing, sorry. There was one big paint in the beginning, and then there are no paints. What does happen is, is compositing. So it's the compositor telling the GPU, you see those paper cutouts, copy them again, blend them again, blend them again, blend them again. A very fast operation. Goes to the GPU distributes it to its different cores to deal with different pixels, with different parts of the screen. So here we do not have a layout. We do have calculate style, and we are still in the main thread. We still change the transform with every frame, which could get slow, not in our control. He was mentioning that Chrome are actually going to remove the hack that people were using with Translate 3D to make the compositing, and we'll just keep will change.
You'll need to use both.
You'll need to use both, yeah. It's a good thing. It's more readable. It's more direct. So here we're still doing this in the main thread because we're in JavaScript land. But before that, where would I not want to use will change? It sounds like, okay, let's use this. This is better for performance. Exactly. This depends on the content inside the layer, whether that changes or not. So where would we not use will change? For example, if we wanted to paint the number of the frame with each frame inside the layer. It doesn't make sense to make a paper cutout because you would have to redraw into the cutout every time and then paint the cutout. You didn't do anything. You just created more memory for nothing. Probably actually you would end up with slower performance. So don't use things blindly. Think of what they're actually going to do. The last way is CSS animations. As there is no painting. It's the compositor doing everything. In terms of painting, this is the same as using will change and CSS, will change and transform. But there is one big difference to CSS animations, which they don't require JavaScript, which means they do not require the main thread. So CSS animations have the potential to always be smoother, because you let the compositor do them on its own together with the scrolling. It goes to a different buffer altogether, frees your main thread. One other nice thing we can do with animation is we can debug them by slowing them down in the animation tab in Chrome. First of all, where we would not want to use CSS animations is when we are interactive. When things move not on their own, but based on events, based on our logic, based on user events. Here CSS animations will probably make things worse. So that's where we would want to use will change with JavaScript directly. Two other ways is Canvas. In Canvas, we paint at every frame. However, we do not layout, and we also don't calculate style. There is no style change in Canvas. So it gives us a way to manage everything ourselves. And in the end, what happens is that we clear the rectangle and draw the image, which is what the browser is going to do anyway. So we do this ourselves. Still, Canvas, when we just talk about images, we want to be careful with it, because when we're declarative, we're letting the browser decide how to paint things better. And here, everything is up to us. Also, we're still JavaScript main thread bound. Where we would want to use Canvas, for example, all I did here is remove the clearing of the rectangle, and we can achieve an effect that you simply cannot do with CSS. Now, WebGL goes to the GPU, which is nice. You can very, very nicely control the GPU to do things fast. You can do really nice games with it. However, JavaScript main thread, not as good as CSS animations. no matter how nice your JavaScript, your WebGL thing is, you're Usain Bolt in the line for the post office. So another thing about WebGL, this is the minimal amount of code I could get to in pure WebGL. There are always libraries, but then you need to load the library to do this. So this is the preparation code. I have to compile a shader, which is the GPU way of rendering pixels. I have to define buffers that define the rectangles and the triangles of what moves around. And I have to define the image and how the image grows and shrinks. It's crazy stuff I need to define. In the end, for each frame, I set the position, and I draw some triangles. Now, this code is actually very similar to the browser code, to the code inside the browser. I wrote that browser code inside Nokia, so it's very much like this. However, when it's in the browser, it's in a different thread, and the browser can control it better. Use CSS. When we want to use WebGL, I'm not very good with 3D graphics design, but this you just can't do with CSS. Like, if you want to do all kinds of 3D lighting effects, things that are actually, you don't have the declarative way of doing them. Games. Usually in a WebGL application, also, it would be very WebGL driven. You would have very few layout changes, very few style changes. You'd be like WebGL like this. The whole system would move around so that WebGL will work nicely. Also, you would do a lot of the calculations inside workers. We didn't really show DevTools much. I showed a little bit the paint flashing, but also use the Chrome timeline and the other things that I'll show in the second part. Analyze your pipeline. Think about it. Think about, is this a layout? How much memory am I taking? Is this going to go to the compositor, or is this going to go to the layout, or is this going to be in the main tabs of the browser? Think about it. Debug it. Plan it ahead. Don't wait until your mobile is slow to plan for this, unless it's too late. Let's plan your render strategy. Consider threading in memory. Think about what operations can move to workers. Think about what operations can be done by the inherent browser threads, like scrolling and compositing. Think about the things. Don't just patch libraries together. Now, this is a rule of thumb, something you can take out of here and actually apply. Think about predictability when you try to figure out which ways of the browser rendering to use. Think about what is dynamic, what is unpredictable. If the content is unpredictable, you don't know, it's user-generated content, it's a post, it's a video. You don't know what this is, or the media meaning the machine. You don't know which phone it's going to go on. You don't know which browser size it's going to go on. That's what layout is for those unpredictabilities. The motion is unpredictable. It comes from the user. It comes from physics engines. It comes from visualizations of data from the cloud. The motion is unpredictable. JSON transforms. Very nice. You want to get wow effects that are not available otherwise, Canvas or WebGL. You're in a predictable world. You want to just patch things to go. You want them to be as fast and as optimized as possible. CSS animations, including transitions, same thing. Just it's a different syntax for the same thing. So this is it. Questions? OK, the question is, are the things I taught different in mobile versus desktop? Usually, they're much more important to look at in mobile, because in desktop, many times you can cheat. You have a lot of power there, and things can look good, even if you didn't use that stuff. You have lots of memory. Usually, you have lots of power. So it's a matter of focus, first of all. Second, you have less memory in mobile. So when you do compositing, you have to know much better what you're doing. Third thing, which is actually in favor of mobile, is that there is no Internet Explorer. I mean, there is, but it's about 0.5% of users on Windows Phone. So actually, 90-something% of usage is Chrome and Safari, which allows, they usually go pretty fast. So the comments here, both of them are true, and I'll expand on them. The old Android browsers, the ones in Android 2 or in 4.1.4.2, are outdated and do not have many of those optimizations. For this, this is what's called graceful degradation. Graceful degradation requires many times more work. But if somebody has an older phone, they would get worse experience. But you have to make sure that it degrades nicely and at least the content loads. I mean, maybe the animations don't work. Maybe you just turn them off. But it's absolutely true. The old Android browser, by the way, does a lot of GPU rendering. It does a lot of things differently, but it kind of sucks too. The other thing is that these are heuristics and hints to the browser rather than actual commands. This is also true. We'll let the browser our intentions and hope that it does best. One of the takeaways about that is try to work in the way the spec has been intended. Keep hacks that are specific to how particular things work at a particular time to a minimum. And the other is, if you do things logically, in terms of planning your rendering strategy, most high chances that the browsers, when they evolve, they would take your approach as a use case they want to keep as fast. But if you keep it hacky, probably not, or you can't rely on it. Also, browser vendors, they do accept bug reports. When I worked on WebKit, we took a lot of bug reports. We took them seriously. At Wix, we talk to them a lot about when we have browser bugs to Apple, to Google. They want to know. Chrome has a very big QA team that can find regressions. If you find a browser bug, it's OK to work around it. But many times you can post a bug, and before you know it, it will be in the browser. Chrome does many updates. Well, we did that several times in front end where we just didn't work around the browser bug, and instead posted the bug to the browser vendor, and saved us a lot of time and makes the internet better, I guess. So the question is, with graceful degradation, how far would I go, considering that it's an if I get you correctly, it's a slippery slope of endless work of graceful degradations for all kinds of browsers. Totally business question. So what I would recommend is in the business context you work in, make good estimations of what it would mean to support different browser and to do graceful degradation. Have good BI, good data about how many people use them. Present them to whoever can make the business decision about it. That's how I have to recommend. What he's saying is that sometimes you would want to pick a rendering strategy also considering test automation. So test automation tool might require better indication from the animation about what's going on, so that it can predict the situation better. It's also a business decision. I personally, when it comes to rendering, I, I, I always try to put the user first, but it's a business decision. Again, I like it to run towards the best user experience possible and to have automation chase me for it if they can't keep up. Sometimes also the browser would have ways to give you harnesses into this if what you need is automation. The new animation API kind of deals with that. The problem is that you always have the chaos theory law. Like the more harnesses you put inside for automation, it changes the original. It changes the original result, especially with things that are so dramatic, like rendering. For example, if you try to do that to measure speed while painting all those paint flashing and frames per second, it will affect your rendering speed anyway. So it's sometimes you have to measure speed separately from trying to debug it. I like using the Chrome timeline for debugging speed. For measuring speed, there is one actual reliable way, which is high-speed camera. In Nokia, we use high-speed camera to measure frames per second regressions. True, you can do the swap buffer tracing. We found in Nokia that in mobiles, it's not as reliable as camera. It's what happens in the swap buffer tracing. You're tracing at a particular point inside the rendering pipeline. If, for example, your GPU is you give the GPU too many commands, it might look to you fast in the frames per second, but when you see it in the camera, it wouldn't be as fast. However, yes, swap buffer tracing inside Chrome, etc., is much more reliable than timeline. But timeline is good for debugging. Like you can see what actually happened, even if it became a little slower than if you did without it.